far we have talked about linear regression only. Mostly linear regression only we have learned. But another most important concept is the different types of linear regressions. Okay, so that's what we call as regression analysis. It's nothing but you estimate the relationship between the dependent variable and the independent variable, what type of relationship exists. Okay, by making use of various plots and all. So there are reference links I have attached which you can go through. I will also open one of these. So basically the goal for regression analysis is we fit a model that best describes the relationship. Okay, and there are actually some say 7 types of common 7 most commonly used linear regressions. Some say 10, some say 15, various. As we go on, I mean, new regressions are being invented, so that's why there could be more than 10 plus different types of regressions so far. So we have listed down several of them here. Okay, linear regression is where you just directly go ahead and see the relationship between the dependent variable and independent variable is linear in nature. That is, if you take a scatter plot, the data is distributed like this, and your job is to fit a line that best describes the maximum amount of variance. Okay, variance is nothing but the spread of the data from whatever the starting point is and whatever the ending point is, whatever the height is, lower height is. So how much ever is the spread is, for that your line should capture all those data points such that those data points are closest to the line. So that is when that happens, so that line is called as line of best fit, and whatever the variance amount of spread it captures, that is called as R squared. Okay, R squared here is 0.77, nothing but 77% of the variance in Y is explained by X. Okay, that is what R squared means. And Y is, as you know, dependent variable, and anything that falls outside of this range is outlier. Okay, and X is an independent variable. Now there for this best line there is always the lower there is something called confidence interval. So that means how far away these points are lying. So how many points can be captured by this line within that particular standard deviation. Okay, so that is called as confidence interval. Okay, so that also is measured. Linear regression we have talked in depth already, but let's moving on. So the second type of regression is called as logistic regression. Okay, logistic regression is again just fitting it's just a variation of linear regression, right? So that means here also you're fitting a regression model to you're just fitting a regression model to capture the relationship between the independent and dependent variables. Now the question is when to use it. Okay, in linear regression, if you go back, so we use it when relationship is linear and whatever the prediction that you are trying to do, it should be a continuous numeric value. That is when we use linear regression. The slight difference between linear and logistic regression is where the first condition should still hold true, that is the relationship still should be a linear one. Okay, and the second thing is the prediction that you are trying to do should be a prediction on that is, it can the ultimate value, target value that you are trying to predict, it should take only 2 values, nothing but binary classification. Okay, so we will see how this works out. But for just to give you an example, one example could be a researcher who is trying to fit a logistic regression model to predict the smoking habits, okay, of an individual who might get a heart attack. Basically, heart attack versus smoking is what is being predicted. So that would become a classical classification problem. Now the way how it works is we will learn this in depth, but for now there is a logistic function. Okay, what happens is on top of y is equal to mx plus b, you fit this function. So whatever the cost function you get, So on top of that, you fit this logistic function. Now instead of you getting a straight line, that line automatically curves at two different places, at above as well as below. Okay, this way, this particular S-shaped lines, we call it sigmoid line. This line can be used to calculate the probabilities. Okay, so lower probability means wherever lower probability signifies the so in this example, for this graph, they have taken the example of insurance, but for talking about this heart attack example, lower probability means lesser probability of getting a heart attack, and higher probability means higher probability of higher values means higher probability of getting a heart attack due to smoking. So this way you can use it for classification, although it's a regression problem, but you're taking a regression problem and fitting it to get a classification value. How that works out, we will see everything in detail, but just to brief it out, yeah. So the third type of regression is polynomial regression. Now in polynomial, what happens is very simple. So see, in linear regression, the data was in this way. Okay, so it was going in one particular direction, so it was easy for us to plot a line through this. Okay, now for logistic regression, for polynomial regression, what happens is the data is no longer in that shape. Either it is like this, it is increasing and going up. Okay, now if you plot a line like this, you will miss out on all these points, or if you plot a line like this, you will miss out on these points. Okay, so there is no way you can use a single straight line to fit this, cover all these points. The only thing you can do is you can start, so for these kind of points, let's just say you have points like this. The only thing you can do is you can take the same straight line that was there like this and curve it, bend it so that it comes like this and goes like this. Okay, now the relationship is no longer linear, it is non-linear, and we already have seen non-linear relationships in the past. Okay, one of those relationship turns out to be a quadratic relationship. So this best fits for a quadratic relationship. Okay, now the equation no longer is linear equation, but rather a quadratic equation. Okay, so that is when if you come across any relationship or any distribution of data points which are in this manner, you will have to use a curved line. Nothing but no longer you can use the linear regression, a slight variation of linear regression by modifying the straight line. The way how you do that is you take this, you add this, this equation is in the form of y is equal to mx plus c. For that you add additional m1x1 plus m2x2 squared. Okay, so that squared will curve that line, line to best fit the data points. Okay, so for example, if someone is trying to predict how many hours worked by an employee is dependent on the overall happiness. Okay, clearly lesser the hours, more the happiness, as simple as that, right? But this relationship is non-linear. But there are some people who also take joy in working up to 5 hours. Okay, some people may not work, but some people take joy of working up to 5 hours because that gives them meaning and makes them more happy. Okay, but if you stretch those number of hours to push it to 7, 8, 10, up to push it to 10, 12, now happiness suddenly decreases. Now if you try to capture this relationship here, so that relationship turns out to be someone, so if it will turn out to be something like this. Okay, if you look at like this, or maybe even like this. Okay, some people, what this means is if you consider this as number of hours and this is happiness, now many people are happy when they are working at a certain lesser amount of hours, okay, their happiness, I'm sorry, I think the relationship is like this, okay, the data points are like this, okay. So their happiness is lesser when they work very less number of hours, because then it would feel they would have some guilty feeling or something, okay. But if they work some certain period of hours, okay, like 5 hours or something, 4 to 5 hours is per day is a good number, so then their happiness will be at peak. But if you increase the number of work hours, okay, their happiness will suddenly fall down. So here maybe they are working like 12 hours or something, but their happiness is too low, okay, something like this. Now you can't capture this relationship with a straight line, so you'll have to use a polynomial of a higher order, okay. So that's what polynomial does. So basically this can be used when we see that relationship between the independent variables and response variable is non-linear, okay, and we have to predict the numeric value, okay. Are you following?
Yes.
Okay.
Yeah.
So
Yes.
when I okay then, so the next type of regression is very similar to linear regression, okay. So next type of regression is ridge regression. Okay. And then we have lasso, okay, and then we have elastinet. We call it elasnet or elanet, okay, elastinet, actually elastic net. So all these three regressions are very slight variations of your actual linear regression that you have already learned, okay. How? The question is how, okay. Let's just say these are your data points, okay, and we have already seen how to control a straight line. You can modify the slope, you can change the intercept, okay. That way either you can start the line here or here or here. You can basically move around the straight line. Somehow you will bring and keep it here, okay. This is what linear regression does. Now what ridge regression does is they have the ability to move this line along its center point. For example, they could move the line like this, sorry, like this, to best capture these data points, okay. Or maybe they could move like this also, okay. So they have all these three have the ability to move the line at their center point here, center point of that line, and best decrease the distance between those data points and the line itself, okay. That is where they are used, and that process we call it as, so something like this. For example, linear regression is this red line, okay. Now if linear regression is giving this line but it is not the best fit line, now what we will do is, in order to move this line slightly around the same place to centrally align on those data points, you will start adding something called as penalty, okay. Now how much penalty is added is where the difference between these three types of regression lies, okay. For ridge regression you add lambda into slope square. Lambda is, again we will discuss about it, lambda into slope square. Slope is again m value that you have already calculated from training data. To that you are squaring and you are multiplying with certain arbitrary value, and there you are adding the sum of squares, sum of squared residuals. So squared residuals are nothing but the loss, okay. To the loss, already calculated loss, mean squared error loss, you are adding additional amount of penalty, okay. Now how much amount of penalty is being added is what is determining the difference. So now for lasso regression you will add absolute value. You won't add the squared value but rather the absolute value, okay, multiplied by lambda, of course. And for elastinet you will add both. You will add two types of lambda, lambda 1, lambda 2, Okay, two different values multiplied by slope squared plus lambda multiplied by slope. Okay, nothing but elastinate is a combination of these two. Okay. Okay, that is where the difference is. Now, when to use this is the question. Okay, so you have to use it when your variables that you calculate the correlation matrix, right? You calculate the correlation matrix and you see that they are highly correlated. In one of our examples where we had to manually select, manually drop out engine based on the engine size, right? So engine
Yes.
CC and a few other factors we had to decide and drop. Instead of that, another approach could have been using the ridge regression. So instead of no longer dropping, keep highly correlated features as they are. Okay, and we saw the multicollinearity was a problem, but ridge regression can handle it. So we no longer drop those features. Instead, keep them and run it using ridge regression. Yeah, and the target variable, you can use ridge regression when it's a numeric value. Okay, for example is also given. So if a basketball data scientist wants to fit a ridge regression model, okay, to predict various variables like points, assists, rebounds, etc., so then they make use of ridge regression. Why? The question is why? Because these points, assists, rebounds, they are highly multicollinear. Okay, so a better player will always have more points. Okay, and they will have more assists, more rebounds. Okay, so multicollinearity is a problem there. Hence, that problem can be minimized using ridge regression. Okay, so is this clear?
Yes.
I mean, just grasp the concept for now. We will see technically what happens. So if you open this link, there is already I have attached the link where they have given much better explanation. Okay, so we call lambda as a tuning parameter. Okay, so this lambda is a value selected by us and multiplied to the value of the slope. Okay, what happens is the whole idea is to add the penalty. When you add the penalty, there is something called model complexity diagram. This diagram, okay, this diagram is very, very important. And when you calculate the residuals, error is nothing but residual, nothing but difference y minus y cap. Okay, every time you hear the word error, just understand it is y minus y cap. Okay, that is what they are talking. Nothing but how far away is your predicted value from your original value. That is error. Now, there is a graph for model complexity. It turns out if you start using linear regression for all the features that you have in the data set, what happens is model complexity, sometimes linear regression, since it's a simple model, it fails to capture the complex relationships. Nothing but your function is not able to get to global minima. Okay, when you understand the concept of gradient descent, right? So we discussed this. So if you are plotting loss function versus m, okay, this is loss function. So if this is your gradient descent and this is your learning rate, okay, you're hopping from here to here, here to here. What happens is if your relationship, if your function is unable to capture the complex relationship between the data points, you will never reach the global minima. Okay, as well as this bias line that you see, we have something called bias and variance. Okay, variance you already know, the kind of distribution that you have in the data set. Now what happens is your model with linear regression, let's just say one relationship, one of the column in your data is having this type of relationship, non-linear relationship, when you fit a straight line to this, here lot of variance, that amount of variance, whatever the variance that is there here, is not captured by your model. Okay, it doesn't generalize well. So we say, that is why we say, in order to capture the variance as well as capture the bias, there is a sweet spot. Okay, there is a sweet spot, and we call it optimum model complexity here, somewhere here in the center. So you can't have a model where you have captured 100% of the variance as well as 100% of the bias. Okay, and in order to have a better model, you have to somewhere hit it in the center. Okay, that is where your error will be minimum. Here, as you can see, this is the bottom of this curve. Error will be minimum here. The error will increase automatically with increase in variance, or error will also increase with increase in bias here. Okay, so if bias increases, error will increase, or if variance increases in the data, your model is so simple to unable to capture all the variance, then also error increases here. Okay, to have least error, you have to have a model with balanced variance and bias. Okay, now that is where
the same diagram. Is it the same diagram what is called as the bias variance trade-off?
yes, this is the same one, bias variance trade-off. Well, there are different representations. Some people also represent in the form of bows and the shooting thing, but this is the official diagram. Yeah, I mean, this was all calculated using experiments, by the way. Okay, lot of data scientists who initially worked on linear regression, they found out this, that the linear regression model is not able to capture the complexity of data relationships between data points. So that's why they came up with multiple experiments. They were able to chart this out. Anyway, so this is where, in case your total error increases due to variance, okay, total error increases due to variance, we call it overfitting. Okay, if your total error increases due to bias, we call it underfitting. Okay, now that can be controlled.
So what will be bias actually? How will we
see, bias is
bias?
Yeah, see, bias is calculated using the training error and testing error. So you first calculate the training error and then calculate the testing error. How much away your points are. Basically nothing but you train the model on training data and then also predict on the training data itself. Then you predict on the validation data set. Now you have two predictions: how your model learned from the data and exhibited the results, and how the model has not learned from the test data set and exhibited the results. You compare both the results. Once you compare both the results, you will be able to tell how your model is doing on the training data set as well as how your model is doing on the test data set. Now when you compare both the things, you will be able to say whether your model is exhibiting overfitting or underfitting. Okay, or in other words, whether your model is exhibiting bias or variance error. Okay, usually, I mean, this is not always the case, but usually this is what is shown. Okay, so first understand what these are. See, variance is nothing but the spread of the data. Okay, your model, if your best fit line represented by the dot, if it's somewhere in the between, okay, then it's done excellent job. It's able to capture all the variance. Okay, that is what we say. But if the spread of the data is somewhere and your line is somewhere, then we call it high variance error. This is high variance error. Okay, and this is high bias error. That means your data is not showing much of variance. Variance is spread again. Okay, but your line is still not able to capture that. Okay, this is the bias variance error. Okay, yeah, this is what we were talking about. So like I was saying, first what you do is, in order to calculate the bias variance, basically, so you can calculate the average here. Okay, you can also write it this way, but usually you can also do it using prediction over the training set as well as the test set. Okay, once you calculate, you will be able to see what is the average bias and what is the average variance. Ideally both should be very similar. Okay, here you can see bias is low, variance is high. Okay, and the average accuracy is 92%. Average loss is 2.30%. Okay, this is for I believe Keras. Okay, neural network sequential model, and this is for decision tree. Okay, fine. So that is what. So there are comparisons that we'll have to do and come to a conclusion whether our model is overfitting or underfitting. Now, in that case, okay, that is where your lasso regression can come in handy. So it can help you understand how much of impact can be reduced. Okay, so whenever your model overfits or underfits, you can use regularization, we call it. So basically nothing but you can use ridge regression. Okay, ridge regression or lasso regression or elastinate. I would say experiment with all the three. If you experiment with all the three, one of them will give you the good result. Okay, so you can choose the best answer. Okay, is that clear?
Yes.
Okay.
Actually, I did not get what is this the variance. We know that it's the spread of the data, but what is the bias that
okay,
I didn't get?
you mean the definition? I mean what it is representing?
Mathematically, what it really represents.
Okay, 1 second, let me see. Bias, bias is nothing but its inability of the model because there is some difference of error. Okay, now let's just say when you do the prediction, your original value, let's just say, let's take a very simple example.
Yeah, I got it. Is it this bias is nothing but the error value between the
predicted
and the actual value?
Yeah.
So that is the difference in the actual point on the graph and the predicted point on the graph and the actual value. That is the difference. We call it as the vertical. We were referring it as a different thing. Okay, fine, got it.
Yeah.
That's the bias.
Yeah, bias is you can reduce it. Okay.
When low bias will be like when most of the points are lying on the predicted line. Actual points are lying on the predicted line, and high bias will be like many points. We are trying to draw the line, but some points on above the line, some points below the line, and then we can just we can say swivel the line around the midpoint of the line, so that we'll try to accommodate as many points as possible, which will be maybe the ridge or the lasso, as you explained now, right?
Yeah.
Okay.
Yeah.
Got it.
Okay. And by using these three, like ridge regression or we can reduce or handle it, right, in best way.
Correct. So usually overfitting is always you can have a better model, which is overfitting model, by using this regularization techniques. For you, see, although mathematically it's a complex or sounds complex, for when it comes to coding, it's a minor change that you will do. Okay, rest model will handle everything. We don't worry how much change to make, where to make, and all of that. We just change one word, simple. Rest model will handle. But mathematically and conceptually, if you want to understand, so we call it L1 regularization term and L2 regularization terms. L1 regularization is nothing but your lasso, and L2 is ridge regression. Now, as I already showed you, you're just changing the direction of the line at its own place, where it has already, I mean, if you had used linear regression, you would have still be able to fit on those data points. But ridge and lasso will allow you to slightly move the direction, move the line at its center point, so that it can reduce the error. That is what is happening, okay, mathematically and conceptually. You can think it that way. Okay, I hope.
So basically, regularization meaning adding the penalty.
Yes.
First, that will have the
yes.
The loss function will be reduced.
Yeah.
To reduce the bias. No?
Yeah. So this is the bias, sum of squared residuals, whatever you're talking about. If you're talking about mean absolute error here, that is y minus y cap, or y cap minus y, absolute value of that. Plus, to top of that, what you're doing is you are adding slope squared multiplied by lambda. So that what will happen is, see what happens when the y cap value increases. See what happens if the error increases. Imagine in the gradient descent form, if let's just say this is loss, basically what is happening is, with ridge regression and lasso regression, what is happening is, if your error is high here somewhere, imagine this in two different steps. This is your normal linear regression. Okay, let me write. This is your normal linear regression. Okay, this is your lasso or ridge regression, lasso/ridge regression. What will happen is, when learning rate multiplied, when you, with your learning rate, you take a step here, you're moving towards global value, global minima, nothing but your loss will be minimum here. Okay, you're moving in this direction. Okay, what will happen is, with the same learning rate, again let's just say learning rate is 0.1 for the sake of argument, 0.1. every time you calculate y minus y cap, you're saying, okay, this difference is still not sufficient, readjust the line. Again, you will go back and change the values of m and c in the equation, then recalculate the value of y minus y cap. Again, you will see the difference is high. Again, you will make the multiplication of this 0.1 into whatever the values of these m and c are. Okay, and recalculate this value. Again, you will go back. Again, you will do until you reach that the loss is quite minimum. Okay, that is what happens in linear regression. This we have learnt. No confusions here. In lasso regression or ridge regression, a slight modification, what is happening is, because you have added the penalty to this term, you have added lambda into some m squared or absolute value of m, you have added. What you are saying to the model is, every time you take a step below here, you are saying, I am still not happy with the calculation of the loss that you have done. Go back further. Instead of this, okay, I mean this rate would be constant, but the amount of loss you have calculated at this point, this is, let's just say L1 for the sake of argument, you're saying this loss is still not sufficient. Even if this model keeps going till here, you will still say that additional loss that you have calculated, I mean the loss you have calculated here, is still not sufficient. So when you each time keep adding this last term, model will have to will further move down. Okay, for instance, in linear regression, it might come till here and may stop here, because further multiplying may shoot here. Okay, it may come here or may not come here, but in this case it will ensure that it will come here only. Why? Because you have increased the loss. Each time what you are saying is your performance is not good, you do go back and reiterate. Again it will keep coming here and here. Again every time it comes here, because you have added this term, you are saying I am not satisfied with the loss you have calculated. You do the calculation, again go back and do it again. So in this case I will mathematically, as an example I'll give you. In this linear regression, let's just say loss actual value was 10. Let's just say original value was 10 here, and here also original value was 10. Now each time this y cap was calculated, let's just say initially it was 5 to it went to 7 to 9 it went, and from 9 it went to 9.6 and stopped. Okay, then when it stopped, when it went to 9.6, you said okay, now the values have reached the global minima. But here what you will say is it will go to 5. You will say I'm still not fine. Go to 9, it's still not 9. Fine. 9.6 still not fine, because there is this extra term here, lambda m square. That lambda m square will ensure that the penalty, that the loss function has the errors are high. Okay, because you have added extra term, the loss is high, and each time loss is high, the model has to reiterate. So it will reiterate here also. Again it will go to 9.8, okay, or maybe 9.9 and stop. Okay, this is how you are able to increase the y cap value and decrease the overall loss. 9.9 is closer to 10, more than 10 is closer to 9.6, correct? So basically you are just playing around with a little bit of mathematics here, and you're saying because of this last term, this extra term, penalty term, you're saying that each time the entire calculation happens, the residuals are calculated. Okay, you're saying this is still not satisfactory, still go and calculate again. So more iterations of calculations happen in ridge and lasso because of this extra penalty. Okay, because of those more calculations, your values will reach the best fit line. Best fit line will be able to capture the data points such that there is loss is less, errors are less. Okay, in
So
this case
this will be so at every iteration that we are going for, say when it is going from 5 to 7 or 7 to 9, at every iteration, because of the penalty term, it will try to capture the best fit line, right?
Yeah.
In this last one.
Yeah, it will keep slightly modifying the angle of that line to reduce those errors. Okay.
Yeah.
So
and
that
from there again it will go for the next iteration.
Yes.
Okay.
Okay. So this way all these three work. All the three: lasso, elastic, lasso, ridge, and elastinet. Now, if all the three work in the same way, why do we need three? Is the next question. Okay. The question is, if all the three are doing the same thing, of course there is slight modification, but if all the three are being used for same, then why do we need three? We could have one single, maybe elastinet, or maybe lasso, maybe ridge, right? There are slight modifications and usabilities of them, where ridge is used versus where lasso is used, etc. So if you want to reduce only multicollinearity, okay, you use ridge, straightforward. Okay. Now lasso, what it does is, because you have modulus of this slope, see, mathematically it's not it doesn't seem like it's a big difference here between the two, but when you apply it on the algorithm, this lasso has the ability to decrease the coefficients completely to 0. Okay, that is the difference. Okay, lasso regression can decrease the coefficients. When we say coefficients, we are talking about m in that matrix equation. Okay, we have that matrix, right? M, then x, then y equals to y, right? This m values, whatever are there, okay, so this lasso regression can make some of them 0. When some of them become 0, all their respective values become 0. 0 into multiplied by anything will become 0, right? Now what is happening is, wherever multicollinearity was there, for example, this was engine cc, this was horsepower, okay, this was weight of the car, because these three were multicollinear and they became 0, the impact of them on the model became 0. Now model can't learn from these three. As a result, it will learn from something else, maybe power of the car. Okay, it will learn only from one of these and not from these three. So the difference between these ridge and lasso is, lasso has the ability to make the coefficient 0 for some of the features. As a result, those features will be completely eliminated. Okay, so what it, in other words, it means is, lasso regression can also do your feature selection. Okay, so lasso regression, if you don't know how to handle the select the features, you are getting confused, blindly use lasso regression, because it has the ability to make the coefficients 0. Okay, so that is one difference, one major difference. Ultimately, all three are used for handling multicollinearity only. Ridge regression, however, it does something else. What it does is, because you're squaring, okay, because you are squaring, see, if lasso regression makes the impact of one value as 0.1 or maybe 1 or 1.2, whatever, because you are squaring this, right, you are using the slope squared term, it reduces the coefficients to near 0 but never 0. Okay, it reduces the coefficients to closer to 0 but not exactly 0. Hence all the features are not eliminated. It can't be used for feature selection, but rather can be used only for multicollinearity. Okay, in order to handle multicollinearity, we can use ridge regression. Lasso regression we can also use for multicollinearity as well as feature selection. Now ElastiNet is a combination of these two. Now if you are again confused, some features are showing too high multicollinearity, some are showing as not good features, you know, in such cases you can go with ElastiNet. Okay, penalty differs here. Okay, up until this point at least ridge regression is clear, and how it is working, how it is shrinking the values, decreasing the error rate. Okay. Yes. Now the exact same explanation applies for lasso also, ridge also, ElastiNet also, by the way. Okay, only the how much amount of lambda you are adding here, lambda term you are adding, that is where it is differing. So between lasso regression and ridge regression, if ridge regression penalizes more, actually it penalizes more because of this square term, but lasso regression penalizes little less. However, it has been observed with a lot of experiments that lasso regression makes the coefficient 0. Okay, as simple as that. For now you can remember that much. And again, lasso regression, like you know, like we already stated here, this is very similar to ridge regression, and it stands for least absolute shrinkage and selection operator. That's what I said, feature selection it does. So that means, okay, so we also call it as L1 norm. Remember this. Okay, this is the terminology used, especially L1 norm. I think we talked about it in linear algebra also. Anyway, L1 norm means lasso regression, L2 norm means ridge regression. Okay,
are we adding this point somewhere, that the generalized thing that the lasso regression has the capability to reduce the slope?
Here we have added. Okay, we have added these points here. Anyway, so what it does is L1 norm. Okay, when you multiply L1 norm, I think we have already discussed. You can again look it up. So L1 norm of the coefficients, what happens is due to the multiplication, so some coefficients become 0. Okay, so that means what in other words is features that are not important, which show very less impact on the target variable, they become 0. Okay, least important features, they become 0. Okay, again, when to use lasso regression? If you have high dimensionality, that means number of features you have are high, like 100 features you have, and you have let's just say 1000 rows of data, but you have 100 features, 100 rows, 100 columns of data you have. You don't know how to reduce them further. You go ahead and use the lasso regression. It can help reduce the model complexity by selecting the most important features. Okay, and how is it doing? By reducing the coefficients. It is shrinking the coefficients to 0, and it can be used when there is multicollinearity, and it can also be used when there is overfitting, when the model has learned only the training data excessively well. That is when you can use the lasso regression as well. For example, someone wants to predict how many years of schooling, how many number of hours worked will give, and what is the cost of living. So basically how many years of schooling and how many years of hours a person is working will determine his cost of living, or better income, basically better standard of life, whatever you call it. So such as you can see, number of hours worked, number of total schooling, they are kind of correlated with the income, especially. Why? Because you will work hard. Again, okay, they don't seem to be correlated. Sorry, they are not correlated, because even a person with no education can work hard. So it's like that. Anyway, so in a case where you have many such features, like you have years of schooling, you have hours of work, you have many other things like health of a person, you have age of a person, etc., etc. Lot of columns are there. You can use the lasso regression or ridge regression also. You can try with ridge regression first, and if you want to further shrink some of the variables, you can go ahead with lasso. Okay, a complete explanation is given here on how it is doing all of that. You can go ahead. So I have already provided the link. Next is elastic regression, or we call it as elastic net regression. Now what it does is it combines both the techniques. Okay, now it is again useful in multicollinearity only. And when to use it? When you have multicollinearity, high dimensional data, when you want a stable model. Very important. This is where the difference lies. So when your model is not sensitive to small changes in the data. For example, if you have too many outliers, then the model is prone to change its behavior with those outliers. Okay, when you want to ensure that model upon introducing lot of outliers also should not change its behavior. Okay, so that is when you use elastic net regression or elastic regression. Okay, so when you want to, when there are too many outliers in the data and you see the model is overfitting or underfitting, go ahead and use the elastic net. Okay, you can experiment with other three also, because all these three go hand in hand: lasso, ridge, and elastic net. But if you see too many outliers, use elastic net. Okay, so one example is I didn't show the code above, but I wanted to show you what is the change, what does it require from you to switch between these models. That is what I wanted to show you. Very simple. When you import these linear models, all it requires for you is to change these words only. Rest everything is taken care by the module. Everything is built in the module. You just have to call it. So instead of elastic net, if I choose a lasso, you will be using lasso, you will be using ridge, or you will be using linear regression etc, etc. Okay, so one example is taken, x value is provided, y value. So based on these 4 features we want to predict price, and when you split it, so here you are passing elastic net. This is the only change you will make. Maybe alpha will be same, but maybe the L1 ratio or L2 ratio you will change here. These are the only 2 changes you will make, but rest everything will remain the same. Okay, so that is what is required from a coder's point of view, but mathematically concept is different behind workings. Anyway, so when you fit the model, you are able to predict on the test, and you calculate, you get the values here. Okay, don't go with the values because I have not normalized this one. No, I have not scaled them. They are on different scales. That's why the error is too high. This is the new mistake we made in the first attempt also, right? Which I showed you, where people go wrong. They don't scale, they don't normalize, they get huge mean squared errors. That is also the case here, but just for the sake of showing this elastic net, I have just done that. Okay, you have to mandatorily scale these things before you feed it to the model. Just remember that. Again, so here alpha is the regularization strength. How much regularization do you want to apply? Here we have taken the 1.0, 100% of the regularization we are applying, and L1 ratio is the mix of L1 and L2 penalties, because elastic net uses both L1 and L2, right? So here it is using 0 as ridge, 1 as lasso, which you can change. 0.5 if you increase it, this will also increase, both will increase actually. Okay, so this way you can run a elastic net model. And
alpha is the regularization strength, meaning is it the learning rate?
Alpha is usually the learning rate, you're right. Okay, alpha is determined with usually the values are in 0.01 etc. But here alpha seem to mean something else. Okay, alpha is the strength of the, see, you are right, absolutely right, alpha is learning rate only, but for other algorithms. Okay, but for elastic net it seems to indicate something else. It's no longer the learning rate. It rather seems to mean that, if you see here, it's directly contributing to that L1 ratio. So okay, it's a plus B. Okay, where A is this first term and B is the other term. So nothing but this is in your y is equal to mx plus c equation. So it's calculating the entire thing. A into,
yeah, this is basically the parabolic, right? Because we are taking y is equal to ax plus b plus cx square.
Yeah,
something like that.
Yeah. Okay, so you can see here, constant that multiplies the penalty term. How much to multiply the penalty? You are anyway applying the penalty using L1 ratio, but how much to multiply it? Okay, so that is what is alpha doing, nothing but increasing the power of this penalty. But you are right. So, okay, alpha is for learning rate only. For other algorithms, like all your neural networks, alpha is the penalty, alpha is the learning rate. Okay, and many others also, by the way. Okay, there are many other parameters you can go through. Okay, these will help you in improving the model. Okay, so this is about
opening that window. How are you opening that window that comes?
Very simple. First, you have to run the entire code, because I ran this code at morning 4 a.m. So after that, you have to type shift tab inside that column, inside that whatever the bracket is, shift tab on your keyboard. You should be able to see the documentation for each of those functions. Okay. So yeah. Okay. All right. So next type of, it's already 10 now. Have you had the breakfast already?
No.
No? Okay, please go ahead and have it. We'll